Okay, so last Tuesday, we had given a formal definition of a random variable. Now, the reason why we require this general property is that we usually use a random variable. Okay, to describe events of interest. Okay, in the following way. And for any interval I of the real line, an event E that the observed value of a random variable x on the sample spaces is in I. So i.e. this event is described in this way, that it's a subset of the samples from the sample space, such that the observed value, okay, under the measurement, because we describe x as a function, can be regarded as a measurement on some characteristics of the outcome, okay? So this is outcome in the sample space. So that the observed values is in an interval. Right? So we require that this subset, okay, should be an event of interest. In F. So that we are able to assign a probability P of E to E, since P is a function on the sigma algebra F. All right, and this is said this event is actually the inverse mapping of the interval under the function x, or under the, okay? And in the context of probability theory, we usually describe this event by this is mathematical expression. Okay, it's to give you a very direct sight on this fact that under the data processing or under the measurement x, the value is in the interval I. Okay, it's in the interval. Okay, so that is the this is a very common way to describe the event of interest by a random variable. Okay, so that so we would like to compute the probability that the observed value of a random variable x in an interval. Okay. Okay. So quite often we have taken an example that if the random experiment is to pick up a student from the NTHU campus. Okay. So the sample space will be the set of all NTHU students on the campus. Okay, so when we do this random experiment, then we have an outcome. The outcome would be you just interview a student on the campus randomly. And you may ask age of the student. Okay, so you may ask, what is your age? And the answer will be a numerical value. I'm sorry. So, and quite often, so the random variable would be the age of the students selected. Okay, and so you may ask for what is the probability that the age of a student is in between, say, 18 to 20. Yeah. 18 to 20 is an interval, right? Or you may ask the weight of a student. Okay? And usually you will see whether the weight of a student is over 80. We consider if a student has weight over 80 to be a fat student. If we don't involve into any discrimination, just yes, please.
So for the age or weight, I won't be the entire real line, right?
Yeah. So if you ask if I is the interval, okay, then you so that the x, which means that okay, so that this description is equivalent to this description. Okay, the same. Okay. So this is usually, we always refer to an interval in the real line if you're concerned about measurement. Okay, for example, what the temperature of a day, okay, and you will consider hot, our what? Our warm, our cold. So you make a range of the temperature, right? So usually we say hot, or may define what is the hot weather in Taiwan, and you will say, well, if the temperature is greater than or equal to 32, for example. And what is the mild temperature? Well, you may think about a mild temperature between, say, 18 to 32. Maybe you define that. And any temperature less than 18 will be considered as cold. Yeah. So you can make a kind of descriptions. Okay. But always, if you think about that, in everyday life, we always referring to an interval of the real line when you consider measurements, all kind of measurements, right, involving asking things like this, okay? A measurement as in some interval, okay? And we would like, if we describe an event by in this way, then we want to be able to assign a probability for that. But to be able to assign probability to such a subset of the sum space, then this subset of sum space should be in the sigma we selected. Why? Because we define probability just on members of the sigma algebra we selected. Okay, so this is the basic requirement that for every intervals, we want this kind of subset to be in the sigma algebra. Okay, so thus we require that the inverse image of an interval under a random variable x is in the sigma algebra F for any interval I in the real line. Okay, now, all right, now since a Borel set B in R, okay, is obtained by countably many operations of complement, union, or intersections on intervals. Okay. So B is so any Borel set, all right, is obtained by doing complement, union, or intersections on intervals. Okay, as we described before. So X inverse of B is obtained by countably many operations of complement union or intersection on the inverse images of intervals under X by proposition (4.1.a). Because in proposition 4.1.a, the inverse function, the inverse mapping, commute with complement, union, and intersections. Okay, so they commute. And right, so once we X, the inverse image of Fourier set B, which is obtained in this way, then is a member in the sigma algebra F. Okay, because every inverse image of interval is in F. Okay, by requirement. So that this is B. All right, and so this proves the following proposition. Okay, so we state that proposition 4.1.b, a function from the sample space to the set of a real number is a random variable on S if and only if the inverse image of any interval I is a member in the sigma algebra F. Okay, so the previous discussion shows that if the inverse image of any interval I is in sigma algebra F, then that every Fourier set, the inverse image of every Fourier set is also in F. And by the definition here, the definition here is that a function from some space to R is a random variable if and only if the inverse image of any Fourier set is in F. Okay, so this is the definition required. Okay, so to justify whether a random variable, whether a function, a real value function on the summer space is a random variable, you justify only this fact. You take an arbitrary interval, and then you check whether the inverse image of the interval is in the sigma algebra we select. Okay, so this proposition is very useful. Okay. Okay, and as you know, that random variables play a central role in the study of probability theory. Okay, so you have, so at the beginning, you have to know the characteristics of a random variable. Okay, the exact meaning of a random variable. It is indeed is a function, all right, on the sample space. A real value function on the sample space. And together with an additional property, right? This property, okay? So this shows that the inverse mapping of X, when we restrict to the Borel sigma algebra, then it will send to members in the sigma algebra. Okay. Any questions? Now we can illustrate a special case. When the sigma algebra we select is the power set of the sample space. Then any function from the sample space to the set of all real number is a random variable. Since the inverse mapping is a subset of the sample space, and then in the power set, because the power set of X consists of all subsets of X. Okay, so in this case, okay, it's quite easy, right? When the sigma algebra you select the power set of the sample space, then any function, okay, it's a random variable. So when the sample space is a finite set, in the finite set, we usually select sigma algebra to be the power set of this finite sample space. Okay, so any functions on a final sample space is a random variable. Okay. So in high school, we usually study random experiments with finite sample space. Okay, and so any measurement on the outcomes of the random experiments give us a random variable. That is true, okay? So in high school, you don't need to worry about the so-called general probability we require here. Yeah, because it builds the situation. But in the situation that the sigma algebra we select is not the power set of the sample space. For example, in our study of the lifetime of light bulb, in that case, the sigma algebra we select is not the power set of the semi-infinite interval from 0 to infinity, because this is too big. Okay, so we select only the Borel sigma algebra, right? On that semi-infinite interval, only the Borel algebra as our sigma algebra. All right, and in that case, then this general property should be verified. Okay, the general property should be verified. And It's very common in many situations that we should consider. The case that the sigma edge we select is not the power state, especially when the summer space is uncountable, right? In many situations, yeah. Then we usually select a sigma algebra which is not equal to the power state of the summer space. Any questions up to now? Right now, so the collection of all events of interest in F which are described by a random variable x, right? So if we collect all the events of interest which are described by random variables, okay? This collection is just the collection of events x in B, which is for all Fourier set B in the Fourier sigma algebra. Okay. Right. So this is a collection, and this collection of interests of events which are described by a random variable is usually, this collection is not equal to the sigma algebra F. Okay, it's just a subset of the sigma algebra F. For example, if we consider the random experiment to pick up a student on the NTHU campus, okay, and if you ask the X is the gender of the student, suppose we using the classical gender or biological gender, say, but there are some exceptional cases, but suppose we have that. So they are all female, all male. So there are only two possible values, and you use 0 and 1 to describe it, okay? So you use 0 to describe the female, and you 1 to describe a male. Now, so that you can describe using the event of interest by sex or by gender. So you may say that, okay, what is the probability that a student on the NTHU campus is a female, or the value is 0? Okay, so what is the probability of this event? Okay, and because that the gender has only two values, so the events you can ask for is very limited, because whether gender is 1 or gender is 0, okay? So that the information you can get is actually very little, okay? Because, for example, you come from the gender, you can talking about something that a female in the EE department, right? Because there is no information about the department unless you use another measurement called y. All right, so y is a random variable which describes the department of a student. Okay. Okay, so that's if you describe event by a specific random variables, then those events of interest, if you collect them together, is usually just a collection of these events. And so by using proposition 4.1.a, okay, it can be shown, which I have put as an exercise in the committee exercise number 5, that this collection is a sigma subalgebra of the sigma algebra F. Okay, so that this collection, we know this collection is just the collection of all events which are described by random variable x. Okay, so this collection is a sigma subalgebra because that it is closed under complement set operations, complement, union, and the intersections. So if you do the set operations in complement many times, then you will be also in the same, the same collection. So it is closed, and so it satisfies the 3 properties of a sigma algebra. Okay, all right. So in the number 5, recommended access number 5, you are asked to show this fact. All right, and this sigma subalgebra will be called the sigma algebra generated by the random variable x, and is denoted, so we use a notation as f of x. Okay, so f of x is a sigma subalgebra of f. Okay, generated by random variable x. Okay, so this is the totality or all the information we can obtain from the measurement x on the outcomes of a random experiment. Okay. For example, if x is about the gender of a student on the NTHU campus, then the sigma algebra generated by the gender consists only 4 members, only 4. The first one is the empty set, the null. The second one is the total event. The third one is the event that a student is a female. And the fourth one is the event that a student is a male. So only 4 members in this sigma algebra generated by the gender measurement. Okay, right. Right. So if the random variable is quite simple, then it will generate a sigma algebra which is quite small. So the information is a little bit only. Okay. Any questions? No? For a random variable x, we usually create a real valued function on R defined by f of x defined to be the probability that the random variable x has a value less than or equal to little x for all x in between minus infinity to infinity. Okay, so this function, this is an ordinary function because it's defined on every real number x. Okay, this function is called the cumulative distribution function, abbreviated as CDF, of random variable x. Okay. So the cumulative distribution function of a random variable record probabilities, okay, probabilities of events like that, okay, and so this is actually so what is this? This is the probability that x in, okay. Right, so as little x become bigger and bigger, then this semi-infinite interval becomes bigger and bigger. And so this event becomes to be bigger and bigger, and the probability becomes to be bigger and bigger. So that's why as x go up, the CDF is going up too. Okay, so that so we can write down there are two simple properties of a CDF of a random variable. Right? The first one is that the function value of a CDF is in between 0 and 1 because it is a probability of certain event. So we know, okay, we know that that the probability will begin of any event will be between 0 and 1. The second property is that if A is less than or equal to B, then we know that this event is smaller than this event. Okay, so that f of A, which is the probability of this event, would be less than or equal to the probability of this event, because this event is bigger than this one. And this is f of B. So which says that the CDF is a non-decreasing function of x in R. Okay, So CDF has these two general properties. Now the focus of this chapter is about discrete random variables. So we will discuss the general properties of discrete random variables. So first of all, what is a discrete random variable? Okay, a random variable x that can take on one of a countable number of possible values is called discrete. So that is a random variable x is discrete if and only if the range of x is a countable subset of R. Okay, so x can take value from a countable set of real values, of real numbers. Okay. Okay, in proposition 4.1.b here, we give a necessary and sufficient condition to justify a function to be a random variable, right? So, which means that we just justify that the inverse image of an interval, okay, under x, all right, is a member of in the sigma algebra F, okay? Right, so this is for general random variable. But if we consider discrete random variables, okay, so suppose x, right, so x is a function, so be a real valued function on a sample space x, and this function have a countable possible values in the set AI in I. Okay, where capital I is a countable index set. Okay. i.e., the range of this function x, all right, is this set. Okay, so suppose that we know we have such a function, a real value function on the sum space, such that the possible value of this function form a countable set here. Okay? So the condition given here, okay, this here is the general function, right, on some space. But the function here, except that it's a real value function on some space, we also know that the function has countably many possible values only. Okay, so this is the possible value of the functions. Okay, so the range, which just means that the range of this function is a countable set. All right, then x is a random variable, and then a discrete random variable. Okay, once it's a random variable, then it must be a discrete random variable, right? By the definition of discrete random variable. So x is if and only if a sub I, x equal to a sub I, so which is it's in F for all possible values here. So the check-in becomes much easier here, much easier here. Okay, you don't need to check any interval I. You just check for each possible value. You just ask for that it is a member in the sigma h by f. Okay, so do you have any question about the statement of this proposition? All right, so if no, I'll give a proof here. Forward direction. So if x is a random variable, then x equal to ai. As we know, this is just the inverse image of this singleton consisted of ai. And we know this is actually the inverse image of an interval. The interval is a cross interval with the same endpoint. So a point is actually a spatial interval. Okay? A spatial interval here. Now it's in F. Things is a Borel set in R. And by proposition, okay, so the Borel set. So because it's a random variable, so the inverse image of a Borel set is in F. It's an event of interest by the definition of a random variable, right? So by the definition, random variable, because x is a random variable, right? If and only if. So if a function is a random variable, if only if that this inverse image is in F. Okay. And a singleton is just an interval just an interval. So of course a singleton is a Borel set, very special type of Borel set. So that is inverse image X in F by the definition. Okay, so by the definition of a random variable. Okay, so this is the forward action. Okay, so the forward direction is simple. Now the backward direction here. So we assume that x equal to ai is in F for all I. Okay, this is our assumption. So suppose we know that this event, this is an event of interest in F. Okay. Now for any Borel set B in R. So we want to show that the inverse image of the B under X is a member in F. Okay. Now, how do we show that? Okay. We let index of sub B to be the set of all indices I such that AI is in B. Okay. Okay. So for any Borel set B, we collect all the possible values AI, which is contained in this Borel set, right? And then we just take out the indices of these possible values. Okay, so this is I sub B. It's clear since I sub B is a subset of the original index set of all possible values. And because I is countable, so I sub B is a countable set. Okay? So for every Borel set B, I sub B is a countable set. Now, since we will see X in B, right? So this is the inverse image of the Borel set B under X. And so that this is the same as okay. So the inverse image of B is actually the inverse image of all the AIs. Okay, so maybe I write here. Okay, so we just consider all possible values, all right, A sub I, which is in the Borel set B. Okay, so the B and this one has the same inverse image. Is that okay? They have the same image. And this set is the union, disjoint union of all the singletons. Okay? This is a countable union because the I sub B, this I sub B is a countable set. Okay, so but anyway, and the disjoint. Now, we know the inverse function and the union is commutable. So they are commutable. All right, so this is by proposition. 4.1.8, okay, commutable. Number 2, okay. Now, and so this is the joint union, x equal to AI. Right, so this set is the joint union of x. And how many events like this? Well, because I sub b is a countable set. Okay. X b is a countable union of events in F. Okay, because each x equal to AI, by our assumption, is in F, and this set is the countable union of events in F, and we know the third property of a sigma attribute gives us that this is also in F. Okay, so this shows that this set is in F. And then is in F. Okay, so this shows that. So for every Borel set B, the x in B is in F. So this shows that x is a random variable. Okay, and that's true. Any questions? Okay. So if no question, then we take a short break up to 2:25. Right. So now, since a singleton consistent of only one real number, AI, it's a minimum non-empty member in the Fourier sigma algebra, script B. This event is a minimum, so it's a minimum non-empty event in the sigma algebra f of x generated by a discrete random variable x taking values in AI okay. So each of these events is an atomic event. It's actually because it's a minimum non-empty event in f of x. Okay, right? So every event is an atomic event, and as can be seen, in the proof of proposition 4.2.a, right? So we move to here. So in the proof of this proposition, we know that for each Borel set, it's a disjoint union of this one. Any member x b in f of x is a disjoint union of countably many events x equal to ai with I in I sub b. Okay, so every members in the sigma algebra generated by the random variable x is the disjoint union of these atomic events. Okay, so that's if we collect all such atomic events together, this is exactly the collection of all atomic events in f of x. Okay. So the sigma algebra generated by a discrete random variable f of x, all right, has a countable collection of atomic events, right? Because the atomic events are just the event that x equal to ai. Okay, so ai. So this is the collection of all atomic events, and this collection is countable because the index say I is countable. Okay. Okay, and specific, in particular, since I sub r equal to I, okay, because every possible value is in the set of all real numbers, so I sub r is just the original set of index, and then we know x is just, okay, so this is the total event, right? Because any value should be a real number, okay? So this is the total event. And so that this is the disjoint union. Okay? So we know that the total event is actually the disjoint union of all atomic events. All right? So this is because you union all index I in capital I. Okay, so this is the disjoint union of all atomic events. Okay, so that the collection of all atomic events is a partition. All right, so it's a partition of the total event x. And then, by the countable activity, that we know one is probability of x is the probability of union. So this is the sum. Okay. Okay, so you can see the original probability function P is a probability function on the sigma algebra F. Now, because we have the summation here, so we know the same probability function is a probability function on the sigma algebra generated by X. Okay, by X, by proposition 2.5.e. Okay, so thus P is a probability function on f of x by proposition 2.5.e. So if we focus on a random variable, okay, then events that can be described by such a random variable is very restricted. Okay, right? All these events will be in here in the sigma algebra generated by X, and this is actually a sigma subalgebra of our original sigma algebra F. So, and in many situations, all right, this sigma algebra will be very simple, very small. Okay? As the example, we took the gender, okay? The gender random variable in the random experiments of picking up a student on the NTHU campus. Okay, and we are lucky because that we only restrict on the event which can be described by a random variable x. Okay, and in our case, if the x is a discrete random variable, then the probability function is indeed also a probability function on this smaller sigma algebra. Okay, smaller sigma algebra. Okay. Any questions? So in many statistical problems or in many science engineering disciplines that you usually provided by a random variable only, okay, and information about the random variables, all right? And so you were missing the sum space, the sigma algebra, and the probability function. But actually, it's hidden only. Actually, you do not miss anything. You do not miss anything. Okay, there's still a hidden probabilistic model in your running in a running experiment related to your specific random variables. Okay, but what you can see through a random variable is the event in here. All right. You can only see the event in here, not in the bigger script f, not the bigger sigma algebra. You can't see more, all right? Because you only describe events by a random variable, okay? But fortunately, the hidden probability function p, all right, is still a probability function on this sigma algebra. Okay, it's still on this sigma algebra, and so that you have so again you have the probabilistic so that's x p instead of the probabilistic model, probabilistic established if only a random variable x is given. Okay. Is observed or is measured, maybe I will say, okay, or observed. Okay. Now, for a discrete random variable x, we define the probability mass function abbreviated as PMF of x as here. Little px is defined to be the probability that x equal to exact the little x. Okay. Now it is clear that the PMF function has value in between 0 and 1, of course, because it's concerned about probability of events. The second, the PMF has 0 values for all x in R, except a countable number of x. Okay. All right. So they may have positive values for when x is equal to a possible value of the discrete random variable. Okay. And third one, if you sum the function, right, for all R, okay, this actually, you have to be careful because the summation has uncountably many terms, right? So how do you do the summation? Okay. Actually, we can do that because the second point, because the function is 0 for all x except a countable number of xi's. So the sum is actually a countable sum, P of AI. Okay? So it's actually, so this sum is actually this sum. Okay? So we can say that this define that because of 2. Otherwise you you can't do the summation at all. Okay? And so this is actually equal to, so by the definition, P at AI is probability that x equal to AI. And the summation, this sum is equal to 1. Okay. So the function, the P of x, the function is that, so you may have, it's zeros. So the value, they are maybe I put here. So this is the function. If you draw a picture of the PMF, then you will see all the values, almost all the value, they are zeros. Okay? Except possible. So in here, this maybe is A1, this is A2, A3, A4, and A5. Suppose we have 5 values there. So that the picture is very spatial. Okay? There's sporadic points, okay, in the upper half plane, okay. So you can see here. And most value, for almost all value of P of X is zeros. Okay, so this is the characteristic of the PMF, okay, the probability mass function. Okay, so you get Now, how about the cumulative distribution function of a discrete random variable, right? The CDF of a discrete random variable can be expressed by the PMF of X as followings. Okay, right? So this is the, by definition, is here, right? But this is the situation that so this is the digital union. AI is an X. Okay, and X equal to AI. So that this is summation. So you can compute the error. So now if we draw the CDF, okay, so that the sum, okay, now here, okay, up here, but now they will come up. Okay, and here it will have a jump of this size. So we know this is P sub A1, this is P sub A2, this is P sub A3, this is P sub A4, this is P sub A5. All right, so it has a jump of this size PA, and it go to here. Okay, and it has a jump here, go to there, has a jump. Okay, so this jump is PA2, PA1, and this jump is equal to PA3, this jump is PA4, this jump is PA5, etc. Okay, so this is f of x. I use the yellow color. So yellow color corresponding to the PMF, and the green color corresponding to the CDF here. So you can see CDF is a right continuous step function. Okay. All right, so which is a right continuous step function with jumps, right, at possible values a sub I of size p sub ai. Okay, so you can see the jump size. So the jump size corresponding to PMF, right? I'm doing PMF there, so you can see that. Any questions? So once you know the PMF of a discrete random variables, then it is easier to write down the CDF of the discrete random variable. Okay, now we talk about expected values for a discrete random variable. Okay. So for a discrete random variable x with possible values a sub I for all index I in the index say capital I. Okay, so for such a discrete random variable, the expectation denoted as E of x, x defined, right? So this is by definition to be the weighted sum of the possible value of this discrete random variable. So a sub I is a possible value, but weighted by the probability that this random variable has a value AI. Okay, and so in terms of the PMF, so this is here. Okay, so if we use the PMF, little p, all right, of the discrete random variable, okay, and provided the sum exists. Okay, so this is a countable sum. So maybe this is uncountable the infinite sum. So you have to consider a series sum. Okay, an infinite series sum, and this infinite series sum may converge or may not converge. Okay, right? So we assume that. But a discrete random variable has expectation if this sum exists. Okay, if this sum does not exist, then we say that this discrete number has no expectation. Okay, so that this is by definition. Let's consider a simple example. So suppose, so let E be an event, and let 1 sub E be the real valued function on the sample space X. So we define a function, right? So if the outcome omega is in E, then the 1 sub E has value 1. But if the outcome is not in E, then the value of this function is 0. Okay? Now, since this event, because it has only two values, okay, there are only two possible values, 1 and 0, okay. Now, this is the okay. So this is subset. But if 1 sub E of omega is equal to 1, if and only if the outcome is in E, so this is actually equal to E here. An event in F, I'm sorry. Let's see. So this is in F, and we check such that. So this is the E complement, which is also in F. So this shows that E is a random variable, okay, by proposition 4.2.8 here. We just check, all right? We just check whether this subset is an event in F, okay? Okay? All right, and this is called the indicator of event of E. Okay? So 1 sub E is a random variable. It's a discrete random variable, and it's called the indicator of E. So you can see that the indicator of E contains information exactly equal to the event E itself. Okay? And so, you see that the sigma algebra generated by this indicator is actually, let me say, here. Very simple sigma algebra you have here. Okay? You have very simple sigma algebra. And the expectation of is equal to 1 times probability of indicator equal to 1 plus 0 times probability of indicator equal to 0. Okay? But we know indicator equal to 1, this event is equal to the E itself. So this is 1 times PE plus 0 times PE complement. And so this is PE. Okay. Okay, so the expectation of indicator of an event E is exactly equal to the probability of this event E. And then later on, you will see indicator of an event is a very convenient tool to study an event because this indicator, this unknown variable contain exactly the same information as E. Okay, because the sigma attribute generated by this one is actually, you can see that the central. So it has atomic events, which is E and E complement. So there are two atomic events there. Okay. Now we talk about functions of random variables. All right. We know. Suppose we have random experiments. All right, and we have an outcome, and by a measurement device X, you get right. So suppose that the X is a discrete random variable. Okay, so you get the value, but instead of using the measurement value directly, we may do the data processing. Okay, say G. Okay, right, and so we have to do something. Okay, so G is our data processing function. Okay, so it's a function from D. D is a subset of R with the range of the random value contained in D. Okay. For example, if G is the logarithm, okay, the natural logarithm function, then D is not the whole real line because D is just the infinite interval from 0 to infinity, right? Okay, and in this case, then the observed value of the measurement should be positive, because if the observed value is negative, then if you apply natural logarithm, it's meaningless, right? It's meaningless. So that the defining domain D, all right, should be a subset of R such that the range of the random variable X is in D. Okay. All right, and in here, a discrete random variable, right? In this chapter, we assume X is a discrete random variable here. Okay, so we do some data processing. Okay, we use that. For example, we take the square of the data, or we take the absolute value of the data. All right, so there are a lot of possible data processing to do it, right? Okay, so this is quite often occur in practical situation. Now, and so we are talking about the composition of two functions. Okay, composition of two functions here. All right, so the composition of a discrete random variable with a function g here. Right? So the question is that a question is a random variable too. So we ask for that. So this is the basic questions. Okay. Is there any restriction to G, okay, for this composition, okay, to be a random variable, specific when the original measurement data, capital X, is the discrete random variable? Okay, so because it is involving composition of two functions, so we need the following proposition about the inverse of a composite of two functions. So let f is a function from A to B, and the g is a function from B to C. Okay. Then we have, okay, so you can see we can do the composition of f and g because the domain of g is the same as the codomain of f. Okay, so that the composite, right? So f and g, and we take the inverse. This is equal to the composition of G inverse and the F inverse. Okay, so A to B to C is F, this is G, and so the composition is G. F here. And now, so if we do the so this is the composition, and and the inverse mapping is a function from the parsecs of G is from the parsecs C to parsecs B. And the inverse mapping of F inverse is set of B to parsecs A there. Okay? And so that we have here. And the proposition says that this composition is just the inverse of this composition. Okay. So the proof. Now for any subset H of C. So we have here X in the, okay, so we look at the inverse mapping of this composite on E, okay. So by definition, which means that G comes with F on X is in E. Okay, so this is by definition. Okay, so this is by definition there. Okay, and but this is okay. The composition means here. All right. So which means that f of x is in the inverse mapping of E under G. Okay, you think about this is y. Okay, this is G of y here. G of y. You may think about this is y. G of y is in E, which means that y is in G inverse of E by definition. All right, and then again, x is in F inverse of G inverse of E. Okay. But why is that? This is just the composition of G inverse and F inverse E. Okay, so you know any member in here is the same as in there. So you show that this set would be the same. So that okay, so we established that we did the same, so that as mapping, okay, so we have these two mapping would be the equal mapping there. All right, so now we are able to answer our question. Let X be a discrete random variable. Then G comes with X is a discrete random variable for any function G from D to R, where D is a subset of R and contains the range of X. Okay. Okay, so for discrete random variables, the data processing G can be any functions. Okay, can be any functions. Okay. The only requirement is that the domain of G, the domain of G contains the range of the discrete random variable X. Okay. Okay. So this is. So indeed, this D. Okay, contains all possible value of a discrete random variable X. Okay. So the restriction is very mild. Okay, very mild. Okay, so I think I stop here, and I have some material to go, so I will give an additional online lecture on Saturday. Okay, not many, but I need to finish chapter 4. Okay, and because our first midterm examination will be next Thursday. Okay, and the starting time is 12:40. Much easier than our regular starting time. Okay, to give you more time to solve the problems in the examination. And it's a crossbook examination, but you can prepare one sheet of paper and you can write everything on both sides of the paper, okay? Okay. If you want to put more things, you can use the smaller character, okay? But you should be able to recognize all the letters. Okay, any questions? Right, so if no questions, then we stop here.